Hello everyone, and welcome to today's presentation. I'm excited to share with you an overview of our 2D building MEP plan, focusing on the layered coordination approach. This slide introduces the key aspects we'll explore, including the unified design layout that integrates HVAC, plumbing, fire, and electrical systems. We'll also look at the formula we use to measure coordination efficiency, the way we compile system quantities for the BOQ, and how each service is installed following specific layers and routing. Finally, we'll cover the importance of testing to ensure system clearance and proper coordination before approval. Let's get started. Let's start by looking at the architectural base layer, which is shown here in gray. This layer essentially forms the foundation of our building design. The design process begins with defining the basic layout, including wall thicknesses, openings like doors and windows, and the grid lines that help us organize the space. A key concept here is the formula for calculating room areas, which is simply length times width. This helps us determine the size of each room and is crucial for planning finishes and other interior elements. Moving on to the bill of quantities, or BOQ, this involves extracting the quantities of walls, doors, and windows directly from the BIM model using specific IDs. This ensures accuracy and helps us manage costs effectively. In terms of installation, we construct the walls according to the dimension plan. Precision here is vital to ensure everything fits perfectly and aligns with our design. Finally, testing is an essential step. We need to confirm that the walls are correctly aligned and that there's enough clear space for MEP routing, mechanical, electrical, and plumbing systems. This step helps us catch any issues early and ensures smooth coordination across disciplines. Overall, this base layer sets the stage for a well-coordinated and efficient building process, linking design, quantity takeoff, and construction seamlessly. Let's talk about the HVAC layer, which is highlighted in blue on our diagram. First, the design aspect focuses on sizing the air distribution system to meet the required CFM, or cubic feet per minute, for each zone. This ensures that every area gets the right amount of airflow for comfort and efficiency. Now, a key part of this is the formula we use. Airflow equals Q times delta T times 1.08. This helps us determine the appropriate duct size. Essentially, by knowing the flow rate and temperature difference, we can select ducts that will handle the airflow properly without being oversized or undersized. Moving on to the bill of quantities, or BOQ, we see that the total ductwork covers about 1,850 square meters. We also have around 220 diffusers and 110 dampers. These components are crucial for directing and controlling the airflow throughout the building. When it comes to installation, the ducts need to be installed carefully with insulation to prevent energy loss. We also install balancing dampers to fine-tune the airflow in each zone, making sure everything is operating as planned. Finally, testing is a vital step. We measure the air velocity at various points to verify that the flow matches our design. If adjustments are needed, we make them so that the actual flow stays within plus or minus 10% of what we initially designed. This process helps us ensure optimal performance and comfort in the space. Let's take a closer look at the plumbing layer, which is represented here in cyan and red. This layer involves the design of hot, cold, and drainage networks, and it's crucial that we get the slopes right to ensure proper flow and prevent issues like backflow or blockages. Now, when it comes to sizing the pipes, we use the basic formula. Flow rate, which is denoted as Q, equals the cross-sectional area multiplied by the velocity. This helps us determine the appropriate pipe diameter so that water flows efficiently without causing pressure loss. Looking at our bill of quantities, or BOQ, we have approximately 850 meters of cold water piping, 420 meters for hot water, 610 meters for drainage, and about 180 fittings. These figures are essential for planning procurement and installation. Speaking of installation, we typically use PPR pipes for hot and cold water lines because they are durable and reliable, while UPVC pipes are preferred for drainage due to their resistance to chemicals and ease of installation. Finally, after installation, it's critical to perform pressure tests on the water lines. This involves pressurizing the system and observing it for 24 hours to ensure there are no leaks or weaknesses. Proper testing ensures the integrity and safety of the entire plumbing system. All these elements, design, sizing, materials, and testing, are interconnected and vital to delivering a robust plumbing layer that supports the overall building infrastructure. Let's now look at the firefighting layer, which is highlighted in red here. The design of this system follows the standards set by NFPA 13 and SBC 807, ensuring that it meets recognized safety criteria. The sprinkler layout is carefully planned based on these codes, with the goal of providing maximum coverage and effectiveness. When we consider the formula for flow, we're aiming for a capacity of 750 liters per minute at 5 bar pressure. This is crucial because it helps us verify whether the pumps we select can deliver the necessary water flow and pressure in case of a fire. Moving on to the bill of quantities, or BOQ, it specifies that we'll need 45 sprinklers, 3 hose reels, and 6 valves. These components are essential for the system's operation and reliability across the entire area. Regarding installation, the main and branch lines will be installed with quick-response sprinkler heads. These heads are critical because they activate rapidly once they detect heat, helping to control or extinguish fires quickly. Finally, testing is an important step, specifically, a hydrostatic test at 1.5 times the design pressure. This test ensures the integrity and safety of the entire piping system before it becomes operational. All these points together form a comprehensive approach to firefighting protection, integrating design, components, and testing to safeguard the building effectively. Now, let's move on to the electrical layer, which is highlighted in yellow on our diagram. When designing this layer, we follow the standards set by SBC 201 and NFPA 70 to ensure safety and reliability. The key here is to carefully plan the lighting and power distribution circuits to meet these codes. A crucial part of this process is calculating the electrical load. The formula we use is the sum of each device's power, adjusted by a diversity factor, divided by the voltage. This helps us determine the total electrical demand accurately without oversizing the system. In terms of the bill of quantities, we estimate approximately 180 meters of cable, 240 meters of lighting wiring, and around 84 junctions. These figures help us plan material procurement and installation logistics effectively. For installation, it's important to lay the conduits before plastering begins, which prevents damage and makes future maintenance easier. Each circuit must also be labeled clearly to ensure proper identification during operation and troubleshooting. Finally, testing is a vital step. We perform both continuity tests to verify the wiring connections are correct and insulation resistance tests to confirm there are no leaks or faults. These steps help ensure our electrical system is safe, reliable, and ready for use. Let's take a closer look at the BIM coordination and data summary. First, all systems are overlaid in 3 dimensions for clash detection. This means we can visually identify any conflicts early in the design process, helping us prevent costly issues later on. Next, we use a clash index, which is calculated by dividing the number of detected clashes by the number we've resolved, then multiplying by 100%. This gives us a clear, quantifiable measure of how well our coordination is progressing. Regarding the bill of quantities, or BOQ, it's auto-generated for each system layer. This automation streamlines our process, ensuring accuracy and saving time when preparing material estimates. When it comes to installation, following the BIM sequencing is crucial for routing. It ensures that each step aligns correctly with the overall plan, reducing errors and ensuring smooth progress on site. Finally, prior to handing over the as-built documents, we validate the 3D coordination through testing. This step confirms that everything is properly coordinated and functioning as intended, providing confidence that the project is ready for completion. Altogether, these points highlight how BIM enables a more integrated, efficient, and precise approach to project management, from design through to handover.